Okay, video lesson number 11, chemical thermodynamics. Now, thermodynamics is the study of heat flow through a chemical reaction or physical process. So remember, thermo means heat, a dynamic is motion, movement, changing. So chemical thermodynamics is the movement of heat. Okay, so there's basically two ways that heat can be moved in a chemical reaction or process, and that is heat going in. That's called endothermic, or heat going out, that's called exothermic. So here's an energy diagram for an endothermic reaction, heat going in. So in an endothermic reaction, notice that we have the energy of the products has more energy than that of the reactants. So there has to be a net flow of energy being absorbed or going in to the reaction. We can also write it in a thermochemical equation. Notice that the energy or heat is on the left side as a reactant. Now remember that in any chemical reaction it takes energy to break the bonds in the reactants, and energy is released when new bonds form in the products. Okay? But what we want to know is the net flow of energy, or that delta H, that enthalpy change. And in an endothermic reaction, more energy goes in than comes out. So there's a net flow of energy in. Okay, so it's an uphill energy diagram, and then delta H is positive. You can think of your bank account. If you have more money coming into your bank account than you are spending, you still have a positive balance in your bank account. That's endothermic. Okay, now exothermic, remember X means exit. This is heat going out. And then the energy diagram would be the opposite. Okay, so here we have the energy of the products having less energy than that of the reactants. So in essence, or in reality, we are losing energy. Okay, so heat must be being released. Okay, and again, you notice the thermochemical equation, the kilojoules or the energy is a product. Remember, we can measure energy as joules, kilojoules, calories, kilocalories. Those are all measurements of energy. In an exothermic process, there's a net energy flow out. It takes energy to break the bonds in the reactants. Energy is released as new bonds are formed in the products, but in this case, more energy is released than it took to break the bond. So there's a net flow of energy out, leaving the chemical reaction. And that's indicated by a negative value on the delta H. And so you can see the energy diagram and the negative delta H. Okay, now what we want to do is calculate how much energy is released or absorbed in one of these physical processes or chemical reactions. Now to do that, we're going to need our equation. Now before we know what equation to use, we need to ask ourselves, is there a phase change? Remember, this was the key question because I'm going to use a different formula for phase changes than when there's not a phase change. Okay? Now how would I know there's a phase change? Terms like melting, freezing, condensing, vaporization, all those, boiling, tell me that there's a phase change. Also, if I don't see a change in temperature, so there is no delta T, that tells me there's a phase change, because remember, at a phase change, there is no temperature change because all the energy goes into overcoming the attractive forces. So when I ask this question, if the answer is no, I use Q is equal to MC delta T, where M is the mass, C is the specific heat, and delta T is the change in temperature. If the answer to this question is yes, then I just need to figure out, am I at the solid-liquid interface or am I at the liquid-gas interface? Okay? So if I'm at the solid-liquid interface, I'm going to use the latent heat of fusion. If I'm at the liquid-gas interface, I'll use the latent heat of vaporization. Okay? And I have my equations there, which I can easily look up on my periodic table, which I had right here. Oh, here it is right here. So they're right here for the taking. So you can use that on the test or quiz. Okay? Okay, so let's go ahead and look at the graph of the heating boiling curve, in this case for water. Now, this is just to help us see where we're at in terms of which formula to use. So now, if I'm heating a liquid, recognize a liquid is right here on the diagram. A solid is right here. And this is a gas. Okay, so when I just heat a solid, liquid, or gas, I need the specific heat. Okay, and that's going to be for water as a liquid is the one we usually use is 4.18 joules per gram degree Celsius. Okay, or else I have to look it up, or that it's given to me in my problem, okay? What I need to know is that these two regions here, okay, this is the solid-liquid interface. That's when I'm going to use the latent heat of fusion, or enthalpy of fusion. And this region on the graph right here, that's when I'm going to have to use the formula for the latent heat of vaporization. Okay, so let's solve a couple problems together. Looking at this one, it says if the temperature of the water rises from 22 degrees Celsius to 27 degrees Celsius, what is the heat of reaction in joules? Okay, so we're trying to find Q. Again, here's my question. Is there a phase change? In this case, the answer is no. There's not a phase change because I don't see words like melting, freezing, boiling, condensing. Do I see a delta T? Is there a change in temperature? The answer here is yes, because it's moving from 22 to 27. So here's my calorimeter. I got my reaction chamber. Heat is being released because my temperature is going up. So I need to recognize that I need Q is equal to MC delta T. So Q is equal to MCAT. This is what we said in class to help us remember it. And then I go ahead and just plug in my numbers. So again, I'm trying to find the heat of the reaction, but I actually don't usually measure that directly in the calorimeter. Remember, here's my reaction. What I'm going to measure is this reaction's effect on the surroundings. So I'm really measuring the temperature of the water. So I need the mass of the water and the specific heat of the water. So Q here is going to equal to 100 grams. And then times that by the specific heat of water, which is 4.18 joules per gram degree Celsius. And then I times that by my delta T. Now this was somewhat tricky. Remember, it's not 22 and it's not 27, but it's the change in temperature, which is the final temperature minus the initial. So that would be 27 minus 22, which would be 5 degrees Celsius. Okay? Solving this, grams cancel. Remember, a side by side, I multiply. Notice my answer is joules. Okay, that's what I want. And so I would do that. It would be 500 times 4.18, which I could do on my calculator very easily. And I would get 2090 or 2090 joules. Okay? Notice the value is positive because I'm really measuring the energy absorbed by the water. That's endothermic. Technically speaking, I was asked about the heat of the reaction, so that was energy released, so this would be a negative 2090 in terms of the joules. Okay? Now, another question, so just moving through a couple of examples, would be something like this. So how much heat in joules are given off when 100 grams of steam condenses into liquid water? Okay, so ask yourself the question, is there a phase change? Answer here, yes. Now, how do I know it's yes? Because I see words like condensation or condensing. I don't see a delta T. There is no change in temperature because there's no temperature change at a phase change. So I need to recognize now, okay, is this at the solid-liquid interface or is this at the liquid-gas interface? And so condensation is when a gas becomes a liquid. So I need Q is equal to M delta H of VAP, or vaporization. Okay, so that was the hard part. Easy part now is plugging in the numbers. So Q in this case is going to be 100 grams, okay, multiplied by the delta H of VAP, which I'm going to look up again on my periodic table. I have it right here. So I look it up on the back, and it is 2260 joules per gram. Okay, that's usually the units we're going to use, at least for our class in this. And then grams cancel, okay, and we can just multiply those together. So that's going to be 2260, and then I'm going to tack on 2 zeros. So that's 226,000. Notice my units is joules. That's what I want because it says energy or heat, right? And again, it's given off, so really that's a negative 226,000 joules if I want to be technically exothermic, right? Now, another problem says how much heat in joules is required to melt 200 grams of ice. So here we ask the question, is there a phase change? Answer, yes. Okay, how do I know yes? Because I see the word melt, okay? I also do not see a change in temperature. There is no delta T. Now, is this between a solid and a liquid, or is this between a liquid and a gas? Well, melting is when a solid turns into a liquid, right? So that means I need the latent heat of fusion, or enthalpy of fusion, which is Q is equal to M delta H of FUS, okay? That was the hard part. Now, easy part, plug it in. The mass here is 200 grams. Okay. I look up on my periodic table, the delta H FUS is 334 joules per gram. I cancel grams. Notice I'll get joules, and then I just do the math. 334 times 200. So I can double 334, right? That is 668, and then I just tack on 2 zeros. So 668, and then I tack on my 2 zeros, or I just type it in my calculator, and you can see that that is 66,800 joules. Just for fun on this one, again, you can notice it's melting, and so the value would be positive because that's endothermic. We could convert this into kilojoules using a T-chart, or we could just move the decimal 3 places to the left, so this would be 66.8 kilojoules. Now, if you find yourself on a test and I ask for kilojoules, you might want to bust out your T-chart, because this is just a conversion, right? 66,800 joules, okay? And then over here I want kilojoules. Notice this is what I'm doing, joules down here, kilojoules here. 1 kilojoule is 1,000 joules. Joules would cancel. Notice I'm just dividing by 1,000, and so I get 66.8 as I move 3 places to the left. You can check that on your calculator. Okay. Last one. So you might see a problem like this. We did solve the metal mystery. You might recall from the lab. There'll probably be one like this on the test, where it says a piece of metal with a mass of 98.4 grams absorbs 849 joules of heat when its temperature increases from 25 to 48 degrees Celsius. Calculate the specific heat. What is the identity of the metal? Okay, so remember, the specific heat is specific to the substance, so we can use that to identify it. Probably the trick here is just to recognize this is what I want. Okay, I want the specific heat. Is there a phase change? Okay, no. Okay, I don't see any words like melting or freezing and things like that. Is there a delta T? Yes. So I'm going to use Q is equal to MC delta T. Okay. Now the only thing here is it's set up to find Q, or the energy. I need to find the specific heat, which is C. So what I would do here is divide both sides by M delta T. Those cancel, right? And so really, and I'll switch this around, C is going to equal to Q divided by M delta T, okay? So now I should be able to go into my problem and just plug in the numbers. So what does it have in terms of Q? That's energy, looks like 849 joules. So I'll put that in there, 849, that's a 9 joules, divided by the mass, which is, and look here, so we got 98.4 grams. Okay, and then delta T. Okay, so be careful here. It's not 25 and it's not 48. It's actually 48 minus 25, right? Which would be, of course, 23 degrees Celsius. Okay. Notice in terms of my units, nothing cancels, because joules and grams are different. Joules and degrees Celsius are different. So my units are joules per gram degrees Celsius. 3 things, but that's what specific heat is, right? It is the energy required to raise the temperature of 1 gram of a substance 1 degree Celsius. So I punch that in on my calculator. So I do 849, okay, divided by 98.4. I like to hit the equal sign here and then hit divided by, not multiply because it's on the bottom, 23. Okay, and I get 0.375. Okay, if I round that, and I try to find the closest thing to that. Okay, so remember, it might not be exact. In this case, it looks like it is copper. Okay, so I would write down copper for my answer, and that's it. So I'm hoping that was helpful. You need to practice the problems. Good luck. I will see you in class.